Hey kids, we're back for another Cinema Verite classic here. Soon to be a viral sensation, I'm sure. I'm almost up to 30 subscribers on my channel, so really killing it out there. Strange that I have 100 students, but whatever. So today here we're going to talk about area between two curves again, but day 2, taking it up a notch. So first question here says, find the area between the y-axis and this curve, which is a sideways parabola, x equals negative y squared plus 5y plus 6. Now, we've been doing the area between two curves and doing it dx, going perpendicular to the x-axis, right? And then you'd have to do the top curve minus the bottom curve. And in order to do that, you would have to rewrite this and solve for y, and then you get plus or minus the square root. You'd have to complete the square to do it, and your top curve would be the positive square root, the bottom of boundary would be the negative square root. So why don't we just do it reverse, huh? That's the idea. If it's in terms of y and we're going to the y-axis, no problem. So just think about this here, because we're going to be doing a lot of things in terms of y. And just remember, any point on this curve here, doesn't really matter which point, that now that we're going to the y-axis, it's the same idea as when we were doing Riemann sums, you know, these infinitely thin rectangles, which are practically line segments, and the height of them was always our y value when we were going to the x-axis. But now that height of that rectangle, or that length of that segment, is the x value. So it's the x value at any given point. You know, a bigger x value, a bigger segment. And the x value is always dictated by this expression in terms of y. So that's really why everything is just flip-flopped. Want the area to the y-axis? No problem. I'll integrate this function, which is in terms of y. And so I'm multiplying by the difference in y. Remember, that's what dy, or differential, really stands for, that tiny difference in y, the width of each rectangle. And your boundaries, your limits of integration, they now have to be y values if you're doing everything in terms of y. So no problem. We look along the y-axis, and it goes from -1 to 6. And that's that. It's that easy. Integrate this by hand, plug in 6 minus plug in -1, and I use my calculator for that, right? Why not? So let's go to math 9 here, classic, going from -1 to 6. And now when you type in your equation, the thing that you can't let bother you is that this equation is in terms of y, but y is just a variable. It might as well be theta, anything else. So when you type it, you still are typing x, but it's just a variable. So sometimes that can mess with you a little bit, but don't let it. Of course, we're doing it with respect to that same variable, and you get about 57.167 if you're a truncator, 166. And of course, on the AP, which is already passed, either one would be acceptable. I'm a rounder. It's just how I was raised. What can I tell you? So the big idea here, because we're going to move to ones now where there are two curves, or maybe 3, and different boundaries, not just going straight to the y-axis, but if you're going perpendicular to the y-axis, you know, those sideways segments essentially, and you're doing it with respect to y, so that means dy, then everything has to be in terms of y. X has to be a function of y, not the other way around. And so I don't know what these values are, we'll just call them a to b. But when you're going vertically and there's two curves, you do top minus bottom. Well, when you're going side to side, now this time I was going to the y-axis, but the idea is that horizontal distance, you want to describe it as a positive thing, a positive quantity, so you would always do the right x value minus the left x value, regardless of where those 2 points were, both on the left side, one on the right, one on the left, you know, wherever you were, right minus left would give you that positive difference. So this is the phrase I'm going to use a lot. Even in that case, the left boundary was 0, so it was just the curve itself. Okay. Hey, one more example here. You know, I couldn't just stop after one. You know, if you're struggling here, you know, throw me on double speed and imagine it's just a really long TikTok video. You'll be done in no time. You're not going anywhere anyway. What do you care? So here we go. Let's find the shaded area, this time bound by this curve. Y equals e to the 0.5 x minus 4. That's this exponential growth with an HA of y equals 4. Nice, right? And this sideways parabola of x equals 6 minus y squared. It's got its vertex at 6, 0, and it's opening to the left because of that negative coefficient. So here you really have a couple different options. And the interesting thing is you've got to kind of make a choice, because this function is in terms of y. It's x equals 6 minus y squared. I could easily solve that for y and put it in terms of x if I like. This one is in terms of x. Y equals this function of x, the exponential function here. So you take your pick whether you want to do dx or dy. If I were doing dx, if I like to do, you know, things in terms of x, well, just keep in mind the area of this region, you know, just think about drawing vertical segments, because that's what you do when you are doing, you know, dx perpendicular to the x-axis. You'd be going like this, and in your top minus bottom would be the blue minus the red, the, you know, the exponential minus the parabola, which would be no problem. Again, you'd have to change this parabola into x terms, so you'd have to solve that for y. But right here, notice after this point of intersection, which has been so graciously provided for you, after this point of intersection, the top minus the bottom, the boundaries switch. You would have to make two separate integrals and split it right here, and your top minus bottom would be the positive square root minus the bottom square root, which is what you would get if you solved this for y. You get plus or minus the square root of, you know, 6 minus x. And so you could do that. It's not something you couldn't handle, but it would require two integrals. It'd be a little bit annoying, but I'd like to do it in terms of y, since that's kind of what we're working on here. But I did want to at least talk about that possibility. And the reason why it's nice to do it in terms of y is because if you think about this region now and we do it in terms of y, we're talking horizontal segments going perpendicular to the y-axis. And no matter where I draw those horizontal segments, here's what's kind of nice. You go all the way through the region, the boundaries never change. The right boundary is always the parabola, which in terms of y is 6 minus y squared. It's always that, no matter which segment I look at. The right is here, the left is the blue, and that's the case down here too. And the blue is this. Now the one thing I've got to do is change that into, I've got to solve it for x and put it in terms of y. So that is really the one thing that's a little bit annoying here, but nothing you can't handle. So here's the equation I have. And I'm not like writing the inverse of it or anything like that. I'm just literally solving this for x. I want it to say x equals something in terms of y. So I'm going to add 4. And now how do I solve that for x? Oh, that's right. I'm going to take the log, the natural log of each side. So I'm going to take the the ln of both sides. Yep, classic. You're going to miss them next year. And you have 0.5x equals the ln of y plus 4. And that's 0.5. You can divide by 0.5 or multiply by 2 if you prefer. Maybe that looks a little nicer. And so your equation is x equals 2 ln of y plus 4. That is the same equation here. It's just now solved for x. And so now I'm going to set up my integral, and I can just do one integral, like as we said, because throughout this whole region, when you do the right boundary minus the left, it never changes. That's why I sometimes like to draw a whole series of these horizontal segments just for myself to see that the boundaries are always the same. Right minus left, red minus the blue, red minus the blue. Okay, so the limits of integration, you're talking about these two intersection points, and you're doing it in terms of y, which means focus on these y values, the y values of the points of intersection. So if you find those things on your calculator, normally you've been looking for x values, pay attention to those y values. So 1.598, okay. Oops, got a little cut off there. So negative 2.195 to 1.598, and the right boundary here, the right boundary is 6 minus y squared. And again, you're just using the portion that represents x. The 6 minus y squared stands in place of x, minus the left. And the left is this expression for x for the blue, which is 2 ln of y plus 4. Be careful to use parentheses if you need to. We don't on this particular one, but if it was had multiple terms, you'd have to distribute that negative, or at least use parentheses. And then dy, all with respect to y. So I'm going to put this in the old TI. I definitely don't feel like doing that one by hand. Lots of luck integrating ln if you haven't taken BC Calc and learned integration by parts. Someday, we were going to do it maybe after the AP, but now we're learning this. Okay, so negative 2.195 all the way to 1.598. And our right boundary, 6 minus, again, we're just using the variable x. That's no problem, minus 2 ln, natural log of x plus 4. Close that ln. Should be good with respect to x. If you get a negative, again, maybe you reversed the boundaries here, because you always want to go right minus left. That's what you're dealing with. And this gave us about 8.306. Beautiful, right? Very cool. For a fun activity this Saturday night, maybe you could do it in terms of x and do the two separate integrals and see if you can get that same value. Very fun for the whole family. All right, kids, you got any questions? Just ask, and feel free to subscribe and like. All right, take it easy, kids.